Don't worry. You know what mine looks like. Mm-hmm.
Okay, good afternoon. Welcome to Oceanography, Principles of Oceanography, OCE 4008. This is week 2. I've recorded a lecture version of the material on chapters 1 and 2, and that's been put into the module for week 1. I think we had issues with the breakout rooms, and the problem with the breakout rooms is if you log in to this Zoom meeting using a non-FSU email account, then I don't know, I can't previously set you up so that you automatically go into a break room. So that's why we need everybody to log on to to join the meeting from their FSU email and to use their FSU email, and that should allow everybody to go automatically into their breakout rooms. So we'll have about 40 minutes or so of lecture, and then we'll try the breakout rooms to make sure that those things are working. So today we're moving into a discussion of chapter 3, plate tectonics. Plate tectonics is absolutely critical for understanding the shape of the world oceans, and the theory of plate tectonics, as we'll discuss in the lecture today, is an example of a paradigm shift, the discovery which alters the playing field for science, for all science in what that follows. And there are many examples of paradigm shifts in the development of science. For example, reaching the understanding that the Earth is actually orbiting the sun along with the other planets. That was a major discovery. It's not obvious from the the observations that you can make from the Earth, but once that was figured out, that was a paradigm shift, and all subsequent science built on that basic idea. There are other paradigm shifts that have occurred in science. For example, the discovery or the theory of evolution fundamentally changed the way we think about how species develop, where the many species of plants and animals come from. Having the understanding the theory of plate tectonic of evolution informs the way we think about new species. And likewise, the theory of plate tectonics changes the way we think about Earth and the climate and development of the oceans, and many other processes follow from that basic discovery. All right, well, let's dive into this. We're going to be talking about the way in which oceans form as continents rift apart and are driven across the surface of the planet by the forces of convection of molten material in Earth's mantle. So oceans are constantly forming, renewing, being renewed, and being destroyed, whereas the continents are remnants of the Earth, which date back to the formation of the planet. What I'm going to show you now is a short video that sort of highlights these different principles. This is from National Geographic. It's kind of dramatic the way it's presented. It's not entirely scientifically accurate, but it gives a good illustration of the principles of plate tectonics that we're talking about and the way that these processes have defined the planet throughout Earth's history. Here we go. Hopefully this will play.
Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper, or the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At First, Cretans and one continent called had the planet all to themselves. Then, around 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? Hell, apparently. The force driving the plates is the slow movement of the super hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, but it wants out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know, or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
Okay, so that was an overview. Was everybody able to see that video? I need to know if videos are transmitting. Can somebody give me a hand or an indication that you're able to see?
Yeah, I can see it.
We can see it.
All right, so that was a National Geographic presentation of plate tectonics, a quick overview of what we're going to be talking about. And you get the idea of this continuous process of movement of the continental land masses. And they're being pushed around by the formation of new oceanic crusts. So what we need to understand is how those processes occur and also how we've discovered them. So we need to think about the following kind of big ideas that are in chapter 3. So a really important idea is this concept of layering, that Earth is composed of layers, that the layers have different chemical and physical properties, and that the interaction of these layers is what produces the plate tectonic motion. We also need to understand that large areas of Earth's continents are held above sea level. They're floating on this quasi-fluid mantle body. We've learned about this continents principally or initially by, so we can't look into the Earth, but we can study waves generated or energy generated by earthquakes, and we can listen to that energy or examine that energy and deduce different processes within the Earth's core. Plate tectonics suggests that the Earth's surface is divided into segments called lithospheric plates. Lithosphere is stony sphere, lithospheric plates, and these plates move, collide, and slide past one another. The force that's driving this process is the heat-driven convection cells within the mantle. So we talk about the mantle as being liquid, but it's only liquid and flowing over time scales that are practically incomprehensible to human beings. But nonetheless, we can understand that this convection currents are what driving motions of the mantle and causing the continents to rift apart and move around. The heat is generated, or the heat is caused by remnant heat that that was energy that was present at the formation of the planet, and also by radioactive decay. About 60% of the heat is the remnant heat, and about 40% of the heat comes from radioactive decay. And then the theory of plate tectonics describes the large-scale features of Earth's surface and the relatively young age of the seafloor. And we'll understand as we go through this chapter how different scientific disciplines and different observations and experiments led to the formulation and confirmation of the theory of plate tectonics. So hold those ideas in mind as we go forward. So we've been talking or tossing around ages and words and concepts like that. So how do we know that the Earth is 4.7 billion years ago? Billion years old? Well, the principal metric that we have is what's called radiometric age dating. And what radiometric age dating does is it takes a sample from the present day Earth and measures the radioactivity of that sample. And that radioactivity is compared to a putative or a theoretical radioactive activity when the material was formed. So the element that's most often used is uranium-235. Uranium-235 has a half-life of about 700 million years. So if we started at a zero age, 4.2 million years ago, 700,000 years later, we have half of the material. 700 million years later, we have half of the material that was there present, and then the second half-life and third half-life and so on. And so by making these measurements, we can get approximate dates for the age of the planet. So this is not based on supposition. This is based, the dating of the planet is based on actual or confirmed by actual data. Now, developing this knowledge was not a smooth process. And as I said, when I talked about the concept of paradigm shifts, the original idea of the Earth was that it was very young and that the events described in the Bible and the timeline implied by biblical stories indicated that the Earth had a relatively young age, something in the order of 10,000 years. I think the original idea was that the Earth was about 6,500 years old, and this was based on the age of the people who were described in the Bible, the characters in the Bible. And so it was thought that it was very young, and that the big features on the planet were a result of various catastrophes that had occurred, catastrophes that would include volcanic eruptions. The Great Flood was referred to as a process which might have excavated some of the channels and canyons that were observed. So this is a concept there. But this catastrophic theory of the Earth began to shift as the scientists and scholars introduced the principle of uniformitarianism. And the principle of uniformitarianism suggests that the past is conserved in the information that's present. So each step in the development of the planet and changes in the Earth has to be related or has to build on previous steps. And so there's a uniformitarian sequence of events that's going forward. If we think about this in terms of what's buried in the past, we can say that the stratigraphic layers of Earth are building on the earliest landmass. So if we go back 2.5 billion years ago to the Archean strata, and year on, year out, the strata build up on top of one another. And so that the uniformitarian principle holds that there's a steady accumulation of material. And then these material are divided by various events and markers into different ages and eras. So we'll get back to this in a second, but this is the basic idea. So we can look back through time, and we can look at the fossils and the other indicators that we have, the chemical properties of different strata, and determine their age, determine that one is older than the other, determine that there's been a change by the changes in fossils that are present. And of course, a great example of that is the occurrence of dinosaurs. So we know that dinosaurs existed up to about 65 million years ago because we can find fossils of dinosaurs preserved in ancient strata. When we go forward, the dinosaurs disappear. And so, something happened, some catastrophic event happened. We now understand that this is probably the collision of a cometary body that hit Earth and caused the catastrophe that wiped out a great deal of life. That going forward, subsequent strata don't have the dinosaur fossils. And we'll see that this understanding of stratigraphic layers was available even before there was any kind of theory to explain how the different strata occurred. So one of the principal proponents was an English or a Scottish scientist named James Hutton, and he asserted that the Earth was mostly static, so that the layers that we saw were preserved. There was a debate, theological debate, and whether or not creation had formed these layers for some purpose to test faith or whatever, and that the Earth. But then there had been subsequent events, floods, volcanic eruptions, tsunamis, etc., that had shaped the surface of the Earth, and that we're leaving changes in this. So James Hutton, was aware of the strata that were present and understood that they represented events in the past, but he didn't have a theory for explaining, why they were present. Another important figure in the development of geology and modern understanding was William Smith. William Smith was sort of a largely self-educated person. He was one of the earliest geologists. He had made a living as a canal digger. So he went around in the late 1700s and early 1800s. The digging of canals was an important activity. And in digging canals, of course, you start at the surface and you dig down. And in the process of digging down, you go from the more recent material into older material. Well, the Great Britain, the island of Great Britain, including Wales, England, Scotland, etc., is special or unusual among different islands in that all of the strata, going back to the Precambrian time, all of the strata are preserved within the landmass of Great Britain. And so William Smith was able to compile a map of different strata, different stratigraphic layers, and show that they had accumulated over time. And the tool that he used for doing this was comparing fossils. He was particularly worked with annamites. These are fossils that resemble the chambered nautilus. And by looking at changes in the characteristics of these fossil annamites, he was able to deduce changes in time. And so this is an annamite, and he didn't really understand how the annamites were evolving or changing, but he knew that if he looked at that if he saw one species disappearing from between different strata, that marked a different era. And this process of accumulation results in some odd conjunctions. So if you look at this picture here in the center, I think most people would agree that the patterns in this rock, this fossilized material, resemble the patterns that you might see in the sand or the mud of a sea bottom. And indeed, that's what this was. However, this sample, this rock, was taken from in the Beartooth Mountains in Glacier National Park at an elevation of about 8,000 feet. So the stratigraphic processes and the evolution of or the development of the North American continent had the result that an ancient seabed was uplifted to exist in present-day mountains. So this process this is an example of uniformitarianism. There had to be some sequence of events that transports or that results in fossilized seabed ending up at the top of a mountain. And that process, was they knew that something like that had to be happening. They knew that it had happened. These early geologists, but they didn't have a good theory for explaining what had gone on. So, this accumulation of strata with these different characteristics, as I've depicted here, gives rise to a more deliberate and classified set of eras. And so we divide the Earth history into a series of eras. The Cenozoic is the most recent, and then the Mesozoic. The Cenozoic-Mesozoic boundary occurs approximately at the extinction of the dinosaurs and many other features. So within the Cenozoic period, we have the rise of mammals and eventually the evolution of the human species. Prior to that, in the Mesozoic period, we have the development of dinosaurs, flowering plants. The evolution of flowering plants is a hugely significant event in the Earth's history, and that occurs about 145 million years ago. With flowering plants, the ability of plant life to diversify and propagate is greatly improved. Then we go back to the Paleozoic, in which evolution of many different sort of vertebrate forms is ongoing. So fishes arise about 440 million years ago during the Ordovician. Fishes are the dominant life form throughout the Silurian period, and then we get insects and so forth. So these processes all go. There's a very important sort of event in this Cambrian, Precambrian period, and this 540 million years ago is represents the time in which the first multicellular organisms developed. So life on Earth probably began about 3.8 million years ago, up until 540. I'm sorry, it began about 3.8 billion years ago. But up until 540 million years ago, all of the life was microbial life, single-celled organisms. And then with this transition into the Cambrian period, we start getting multicellular organisms, and with the multicellular organisms begins the evolution of the life forms that we know today. And with this evolution, the Earth is transformed in fundamental ways. And so the accumulation of material, the plants and animals that are living very much influences or determines the kinds of stratigraphic material that's deposited. Okay, so we've talked about different layers, and this we're going to delve into the processes that are driving plate tectonics now. And to do this, we have to think about fluids and density, and this is a concept that's going to come up again and again in oceanography. So let's spend a little time thinking about this. If you have a balloon filled with helium, you ask and you let go of it, it's going to rise to the surface. Well, what's happening there? And everybody kind of understands that helium is less dense than air, and therefore the balloon floats upward. Well, there's an important distinction that we have to make, and this is probably familiar to many of you, but it's an important distinction to identify, and that is that the balloon is rising not because it's floating. So the force that's driving the balloon upward, the helium-filled balloon upward, is the difference in pressure, the density of pressure on all sides of the balloon. Because the balloon is less dense than the surrounding air medium, the air tries to fill that density void, and it can't fill it because there's a boundary there. So that the sinking air gets under this helium balloon, and it's the sinking under that drives the buoyant object upward. And so that idea that heavier things are sinking, and that as they sink they displace lighter objects, is the fundamental way in which density and density stratification occurs. And we commonly apply this and we will be applying this to the atmosphere, to the ocean. But as we've seen with this idea of continents floating on and the ocean crusts floating on the mantle, we can see that this applies at planetary and cosmic and stellar scale. So this process of density stratification is a fundamental to our understanding of fluid bodies, including the ocean. And so we talked about this earlier, but there's this concept of isostasy. And isostasy says that the less dense object is going to sit higher on the supporting medium than the denser object. And so the example of the denser object is in this case, is a ship loaded with material. And so the density, the weight per area or per volume of the ship is greater when it's loaded than unloaded. And so it sinks further down in the water, finds a lower level than the unloaded ship. And so this concept applies to the two different crustal material. So there's a sea floor, and the ocean crust and the sea floor, the ocean plate has an average thickness of about 8 kilometers and an average density of about 3 grams per cubic centimeter. The continental land masses, the ocean floor, ocean continent is largely made up of basaltic rock. The continents are made up of granitic rock, and they have a density of about 2.7 grams per cubic centimeter, so less dense than the ocean, and so and they're thicker. Continent has an average continental landmass has an average thickness of about 35 kilometers. So this lighter, less dense, thicker material floats higher on the asthenosphere than the ocean crust does. So this layering extends to things that are floating on the top. And so if we look at this sort of this cross section, not to scale, and somewhat we see that the asthenosphere, these conduction cells migrating upward, generating new crust, which spreads out from the spreading center and moves across or continually opens. So as the spreading center is opening, new ocean crust is generated, and the continents are pushed apart by this material. The critical boundary, a critical distinction is the boundary transition between the brittle lithosphere, the brittle ocean and continental crusts, and the ductile upper mantle. And so the upper mantle can conform, can deform, can bend and move and flow over very long time periods, whereas the continents and the continental crusts and the ocean crusts are brittle, and when they are moved and deformed, they fracture, and those fractures remain and provide evidence of processes that have occurred. So how do we know all this? The global distribution of earthquakes gives us some evidence for the dynamic processes that are occurring within the Earth. So here's a map of the frequency of earthquakes around the globe, and you can see that they're not uniformly distributed. In fact, they follow some very distinct patterns. You can see that there's a lines of earthquake activity that proceed through the different ocean bodies. So you can see, for example, within the Atlantic Ocean, there's a line of seismic activity, very tightly defined, that flows from the northernmost portion of the Atlantic Ocean all the way down to the southernmost portion. And we'll see quite soon that this mid-ocean ridge is where the new ocean material is emerging from the mantle and causing the ocean to spread apart and to further separate the North and South American continent from the Eurasian and African continent. So, and then you'll also see that there's a pattern of earthquakes on the land margin on the far side, the western side of the Pacific Ocean. You can also see there's a pattern of earthquake activity along the west coast of North America and the west coast of South America. These, this seismic activity is not the result of seafloor spreading, of new seafloor being formed, but it's the result of old seafloor being subducted under the continental boundaries. So how do we know this? And how do we determine this? One of the instruments and the key instrument for the way in which people gained understanding is the seismograph. And so how does the seismograph work? Well, a seismograph is essentially a paper chart idea. There's a rotating drum with a chart on it. And over time, as the drum rotates, a line is drawn to record what occurs. Well, when there's an earthquake or a shock, the ground is moving more rapidly than the recording pen, and so over time, we can see time is going forward. The earliest waves to reach the recorder were the surface waves, followed by S waves, followed by P waves. So these are different, energy packets that are arriving at the seismograph in different time sequences. So there's an event, the event, and the first energy, the first evidence of that are surface waves, followed by shear waves, followed by pressure waves. And these three types of energies have different properties, and these different properties tell us something about the medium through which they were transmitted. In other words, the Earth. So how do these different waves distinguish? So the P waves, the pressure waves, are able to are stopped by liquid bodies. So pressure waves are not, pressure waves are transmitted both through fluid media and through rigid media. And so the pressure waves can travel from, can be detected when they're transmitted from one point on the Earth's surface to another. Whereas the molten core tends to stop S waves. So P waves are transmitted through the Earth, S waves are transmitted or limited to the transmission through the surface layers of the Earth. So the evidence that the Earth was layered came from developing a network of seismographs, so that seismographs were distributed all around the world. And when an event occurred, by noting the time at which these different kinds of waves arrived at the seismograph and comparing those times, the early seismometers were able, or seismologists were able to deduce information about the core. And so in the early part of the 20th century, that understanding was reached that there was a mantle, that there was a rigid outer layer, and that there was a core, and in fact an inner core. S waves cannot penetrate the Earth's liquid core. P waves are bent as they pass through the liquid outer core. And some of the scientists who worked on this, Richard Oldham was the one who deduced that there was a liquid core. And then a Danish scientist, Inge Lehmann, made a more detailed analysis and concluded that there was a solid inner core. So the outer core is iron, and the inner core is iron and nickel. This is an immensely dense area. This is heat of this inner core is approximately the same as the heat of the outer layer of the sun. So there's a tremendous energy content within the center of the Earth. So why is the Earth layered, and what are the characteristics of these layers? Well, as I said, the continental crust is composed primarily of granite, has a density of 2.7 grams per cubic centimeter. Ocean crust is basalt, 2.9 to 3 grams. And then the inner mantle is much denser, which makes sense. It's floating, it's further towards the center. It's composed of silicon, iron, magnesium, has a density of about 4.5 grams per cubic centimeter, and the actual core is made out of iron and nickel, and it has an immense density of 13 grams per cubic centimeter. Each layer is denser, each deeper layer is denser than the layer above it. What are the properties of these? The lithosphere is relatively cool, relatively rigid outer layer. The asthenosphere is the hot melted material which can slowly deform and flow. So the mantle is denser and flows more slowly than the asthenosphere. The outer core is very dense, liquid, extremely hot. The inner core is solid, extremely dense, and extremely hot. So when we examine the physical properties of the Earth's layers, we see that cool, rigid, dense layers float on a hot, slowly moving, more dense layer. So this principle of stratification with deformation occurring because there are convection currents within the mantle is fundamental to understanding the processes that drive the Earth. And so this principle of isostasy implies that when you have greater relief above the sea level, that relief has to be supported by deep roots. So high mountains have to have deep roots, and so this is the a principle here to get to support an elevation above the high above the sea level. You have to have a deep layer to support that mass. And so mountains, then it's implied, are where the continental layers are the thickest. And we see part of that relief in the elevation of the mountains, and that elevation extends into the mantle. So this is that's a sort of a picture of where things stood. Understanding of these and coming to understand this took a long time. And at the turn of the 19th and 20th century, the idea of uniformitarianism had been applied to many geologic questions, for example, glaciation and sedimentation, etc. But there was no good explanation that everybody accepted to understand why the ocean basins were present. There was little evidence to contradict the notion that what we were seeing in the present day was the same way that the Earth had always been. Well, that began to change with some ideas introduced by a scientist named Alfred Wegener. So Alfred Wegener, who was not a geologist, he was in fact a meteorologist, and also one of these sort of Renaissance people that embraced many different kind of scientific disciplines. Well, he looked at the shape of the planet and deduced that he observed that South America fit very neatly into the west coast of Africa, and he proposed that the present-day continents were the result of breaking apart of a unified landmass, which he proposed be called Pangaea. And his idea for how this was occurring, he thought that the continents were broken apart due to the centrifugal forces of the rotation of the Earth. His ideas were not accepted initially. In fact, they were dismissed as sort of crank ideas. And Wegener spent his entire career trying to amass evidence to prove that. And much of the evidence that he collected was valid. So he showed that there were different fossils, that the fossils indicated that land masses that were currently separated had previously been joined. He also looked at the shapes as noted, but the mechanism that he described, or the mechanism that he proposed that was driving this, what he called continental drift, simply was not sufficient to move the continents apart or to form new ocean areas. And so, although his theory was, or his ideas were correct in their application and in their consequence, they didn't really apply, or they were not consistent enough to stand up. So the prevailing idea, which existed right up until the late 1960s, early 1970s, was that Earth was sort of shrinking like an old apple, and as it shrunk, the ocean basins and the mountains were sort of the skin of the apple, kind of wrinkling up to accommodate this loss of mass. And so that was the prevailing theory up until the early 1960s. That suggested why. What evidence is there? So this is the idea. So he proposed that there were glacial deposits on portions of continents that are currently warm. He noticed that there are the alignment of geologic features such as mountain beds, that when you reassemble the continents, you get this. He also found that there were identical fossils of the same age on land masses that are no longer connected. But he, as I said, did not have a mechanism that could explain this. It's this idea. Well, what are some examples of these? And a good example of fossils and animals indicating connection between land masses that are now separated can be found if we compare monkeys. So monkeys are primates. They've been around for 20 or 30 million years, monkeys are found on both the African continent and also on the South American continent. Well, the old world monkeys are characterized by, they have prehensile feet and toes, but their tail is just a tail, whereas New World monkeys, so they're able to, this is an old world monkey reaching down, and whereas a New World monkey has evolved to the point where its tail allows it to grasp objects. And so this evolution of a prehensile tail must, Wegener proposed, have occurred when the monkeys that separated from a common ancestor evolved on separate continents. So how can we test this hypothesis? So Wegener's hypothesis of continental drift explained the observation that the portions of the continent seem to fit together, but there was no way to perform an experiment that would prove it. And that's an issue for geology and for all earth scientists, earth sciences, is that we really can't experiment with the planet the way we do with chemical processes in a laboratory or biological samples in a petri dish. So we can't alter the conditions that influence the development of the earth as we understand it. We can't perform experiments to do this. So what do we do? What do earth scientists do is they make careful observations and very exacting and quantitative, and then they compare those to different theories. And so Wegener's hypothesis, and ideas, couldn't be confirmed by observations that he was able to make. And Wegener, in fact, died during an expedition to Greenland in the process of trying to locate more fossil evidence to help prove his theory. Well, the person who really solved everything was a Canadian scientist named John Tuzo Wilson, and he proposed the theory of plate tectonics to explain the same set of facts that Wegener had observed. And so the puzzle piece, the collection of the connection of the continents, the similarity of ancient fossils, and the formation of new ocean basins, was explained by the idea that he came forward with. And there were a number of key observations that he made, and by putting these observations together and by telling a more plausible story or formulating a more plausible theory, he was able to come up with an idea that actually fit together in terms of to explain what was happening. And we're going to go through some of the critical ideas that he proposed. And so this was all, fairly recent, well, recent for me, 1966. And it's remarkable to think that as late as 1966, we still didn't have a clear idea of how the Earth was operating. And so, all the things that, that follow from that, were limited by that lack of understanding. So what did Wilson do? He looked at seamounts and hotspots. He looked at the formation of the joining of different continental land masses, and he looked at a C4 feature called transformed faults. So how do these things fit together? Let's see. So the development of plate tectonics was enabled by various key technologies, the seismics, the ability to measure and categorize large-scale earth motion, precision depth recorders, which accurately measure the ocean depths from a moving ship, magnetometers, which measure magnetic charge of the seafloor, and also submarines, human-occupied submarines, which were able to go down and make direct observations of events that were occurring at the bottom of the ocean. So, this is a precision depth recorder, and in the old days, measurement of the ocean depth was done with a lead line. So you would lower a line over the side of the ship, and when it hit bottom, you'd measure the length of the line, and that gave you the approximate depth of the water, not accounting for the angle and everything else. During World War II, they developed a technology that made a measurement based on sound. So a pulse is transmitted from the ship. It travels through the water, hits the ocean bottom, and reflects, echoes back to the ship. Well, if you know the time between the pulse being emitted and the echo from that pulse returning, and then you know the speed of sound in water, you can take that time lag, divide by 2 for the transmission and return journeys, and come up with an accurate picture of the depth of the water. So we'll assume that the speed of sound in water is about 1,500 meters per second, and the delay between the transmit and receive divided by 2 is equal to the depth. And this is characterized in two-way travel time. Well, this is a precision depth recorder with a paper chart. Nowadays, of course, everything is electronic, so you wouldn't have had this paper. But when Wilson was active, this was the technology being used. So here is a record of the depth as a ship is going from east to west across the Atlantic Ocean. And you can see, so here's the depth going along, and you can see that the depth decreases and then falls away, and there's a sort of a little valley here, and then it rises up again on the other side. And so ships that were able to make these profiles of the ocean depth reported this feature, this sort of axial valley transcending the middle of the Atlantic Ocean, and that this ocean depth was present everywhere. So this feature is called the Mid-Atlantic Ridge. And here's a picture of the Mid-Atlantic Ridge. You'll recall that I showed you that a map of the distribution of earthquakes. Well, the distribution of earthquakes very closely tracks the line of this mid-ocean ridge. Well, Tuzo Wilson, took the evidence for this, and he took in particular these fault lines. These are cracks in the ocean floor that are parallel to this canyon, and he deduced that these transform faults were necessary to to accommodate for the motion of the plates on a spherical surface. And so these transform faults, Wilson realized, were evidence that there was new seafloor being generated or new ocean crust emerging along this, this mid-Atlantic ridge, and that as it moved apart, these fractures, these perpendicular fractures had to form in order to accommodate the motion of the relative motion of the two plates on a spherical Earth. So this fit Wilson's hypothesis. So this observation was consistent with his idea that that new ocean plate was being generated, that its motion was driving the continents apart. So that was consistent. But one had to still ask, you know, are these plates actually moving? Is this really occurring in the present day? Well, evidence for this, Wilson said, came from looking at volcanic island chains. And the biggest example of these volcanic island chains is the Hawaiian island chain. And the Hawaiian islands are present over a hotspot. And hotspots are not super well understood, but the basic idea is that there's a plume of mantle material, a very large plume of mantle material, and this is rising up to the ocean lithosphere and emerging volcanically at a fixed point on, within the Earth's sphere. And so, there's a constant, in geologic terms, a constant eruption of new material occurring at this precise point on the planet. Well, if it was the case that the plates were moving, you would expect that over time there would be a series of volcanoes that would form, and that's in fact what we see. So there's the Hawaiian chain of volcanoes, and then there's the Emperor Seamount chain of volcanoes, and the most recent volcanic activity occurs in the present day Hawaii. And in fact, as recently as a couple of weeks ago, a new eruption of the Kilauea volcano has started to occur. And so there's constant eruption, but as the plates move, the material that accumulates as a result of those eruptions, the volcanic islands, are shifted away from the hotspot in the direction that the plates are moving. So the direction of plate movement, the formation here, and then increasing age of volcanoes as you move further from the origin hotspot. So that was another line of evidence for So we can see this, these mantle plumes occur in different areas. There's a mantle plume in Hawaii, as noted. There's another mantle in the Snake River Basin, and so over time, these hotspots are events that create volcanism at specific points. We can see, we can get a good look at how this mid-ocean ridge appears if we look at the island of Iceland. Iceland is a hotspot, and it's a hotspot that occurs right in the middle of the mid-ocean ridge. So the hotspot has caused a landmass to form over the top of the material, and that hotspot is occurring right on the ridge there. So this is a view, an aerial view of this mid-ocean ridge, that bisects the entire island. And so you can see those same features that we saw in the seismograph, the steep mountains on either side, and this axial valley present exposed to air and visible to people. So these kinds of features, being able to measure these features in the ocean and then observe similar features on land, provided additional evidence that the planet was occurring. Okay. So here we have a picture of the ocean landmasses, and you can see these continuous, so the spreading centers go all around the globe. They're all sort of connected. You can draw a connection from one spreading center to another, and they tend to occur in the middle of ocean basins. And spreading centers are typically bisected by these transform faults. So you can see, here's a spreading center in the Southern Pacific, and there are transform faults all along that spreading center. Likewise, so anywhere you see this line of relief with spreading centers along, with the transform faults along it, you know that you're looking at an area where new seafloor is forming. The formation of this seafloor, and as this ocean crust emerges, it pushes the continents further apart. And so here we can see, using satellite bathymetry, these transform faults. And, so this is the axis of the mid-ocean ridge. Here's this fraction here. And the new ocean is spreading apart. So, this observation of, putting the evidence of the island arc chains and the transform faults together, was also tended to be confirmation of Tuzo-Wilson's theory of plate tectonics. But as late as 1965, in the late 1960s, scientists were still not convinced that these things were occurring. So this diagram explains, why it is that you have to have these transform faults if you're forming a new ocean crust, so that the motion relative to any, on a spherical body, motion here is less than the motion here, and so to accommodate that, you have to have this transform faults. So transform boundary features are offsets oriented perpendicular to the mid-ocean plate, and the segments of plates are sliding back and forth. And this allows the mid-ocean to move apart at different rates, and the process of this fracturing and creates different features. Okay, so that was evidence, from these observations, but it was still difficult to convince prevailing scientists that these processes were ongoing, that this wasn't just remnants of things that occurred in the past, but that in fact plate tectonics was an ongoing process, continually shaping and reshaping the structure of Earth. So that critical bit of evidence, was still lacking. So where did we get that evidence? Well, it came from looking at the magnetic properties of the sea floor. And so there's a process called paleomagnetism, and in the 1950s, instruments and ability to measure the orientation of magnetic orientation of rock samples was developed. And in the process of doing so, around mid-ocean ridges, it was discovered that there were a pattern of magnetic anomalies, a sort of a regular pattern of north-south magnetic stripes. So how did these occur? Well, the Earth has a magnetic field, there's a magnetic north and a magnetic south, and the present day we have a magnetic north near the in the northern hemisphere, relatively close to the North Pole, but periodically in geologic time, this magnet reverses itself. And so there's a magnetic reversal, and the magnetic reversal apparently occur pretty quickly, over periods of a few thousand years or even less. In fact, the magnetic North Pole has actually been migrating at a greater rate in the past couple of years than in previous time. So when this magnetic north pole, when there's a reversal over time, the rocks formed by eruption during one magnetic orientation will be different from rocks formed by material that's erupted in a previous magnetic orientation. And so so here's the basic idea. In a normal magnetic field, there's the rocks are oriented in one direction. When there's a reversal, the magnetic fields are flipped, and then in previous eras, when in previous reversals, the rocks will be oriented in a different direction. And so if we look at measurements of the mid-ocean ridge, it turns out that there is a striping of magnetic orientations on either side of the ridge. So the present day magnetic orientation conforms to our present magnetic north. But if you go back 3 million years, there was a reversal. And that reversal is preserved in the magnetic orientation of samples. And so moving away from the supposed origin of this new crustal material toward the into older oceans shows this series of reversals. And so this was collecting these rock samples, measuring their orientation, provided evidence that material was forming through eruptions over a sequence, and that sequence coincided with material spreading further and further apart from the spreading center. So that was additional evidence for a formation of new ocean crust, over the past several million years. So when Earth's polarity reverses, the polarity of the new material changes. And by measuring these reversals over time, we can understand how new rock is forming. And then these changes are also present in looking at radioactive decay. So radium-238 is a decay product. And as you move further and further apart, you would expect to have older and older ages. And so as the capabilities for radioactive age dating began to take shape, geologists were able to measure older and older material. So there was an accumulation of ideas. Well, Wilson's concept was that the continents break apart and that they rift apart in the central region. I think I'm going to stop my lecture here, and we've got about 10 minutes left, and I'd like to, I'll continue this on Thursday. What I'd like to do now is to open up, we've gone through the concept of stratigraphy. We've talked about how the principle of uniformitarianism and catastrophe, explained a lot of observations that were made, but a big theory linking everything together took a long time to develop, and in fact didn't emerge until more than about 50 years ago or so. Okay, so I'm going to stop here. And what I'd like to do now is to open the breakout rooms and have you all go in. It looks like everybody is assigned to a breakout room, so that's great. And I'd like you to all get into your rooms and have a discussion, have a look, and you'll see that there's a new team homework that's been assigned. And you can talk about that and make sure everybody's on the same page. So let me open all the rooms and go ahead and get together. So go ahead and join the rooms. If you're having difficulty joining a room, go ahead and put something in the chat. Joshua Castillo, are you present?
I wasn't here for the first class. I don't know how to join the breakout room.
Brandon?
Yes.
Okay. Oh, so you haven't been assigned. Let's see.
Oh.
So you just joined the class recently, or you were?
Yeah, I enrolled on Friday.
You enrolled on Friday. Okay, so you haven't been assigned yet.
Neither have I.
Huh?
Neither have I. I'm in the same boat. I joined the class yesterday.
Okay, okay.
Me too.
All right, so I've got Brandon.
But I emailed you on Canvas and you put me in, I think, group 9. It just says 9-Wilson. I think that might.
I'm sorry, who?
That's Brandon, sorry.
Okay, so let me put you in group 9 then.
Okay.
Chase, I'll put you in group 10. Jasper, I'll put you in group 11.
Actually, I believe I'm in group 4. I just don't know how to join. On my Canvas is set. I'm part of like group 4, this Nazi sea slugs, I think.
Okay, Jasper, where did I put you? Okay, you're in group 4?
Yeah, I believe so.
Yeah, so everyone's assigned a group on Canvas, but I think I'll have to update that spreadsheet for you now that AdDrop closed.
Okay, so Jasper, you should be able to join. There you go. And Joshua, can you join group 5? And then I've got one person who's in, I think, by phone. Can you identify yourself? Somebody's on by phone. I don't know who that is. Okay, and then Jesse Nikija.
I was in group 1 on my Canvas. It says Tiger Sharks.
Group 1.
Thank you.
Jesse. There you go. And I'm going to put you in team 11, Carrie. I'll put you in 11.
Okay.
A Google Doc, right?
Yeah.
Hi.
So your Gmail.
Are you guys, do you have a plan for how you're going to be able to work on documents together? Will you be using Google Docs or OneDrive?
Yeah, we're using Google Docs.
Okay, and that's working for you?
Yeah.
That's how you were able to do turn in your assignment already? Okay, great. Well, all right, I'll, so you'll see that there's a question for the team homework where I want you to go on to Google Earth and look at Google Earth and go explore around the ocean basins and try to learn and see what you can deduce there. And so you might have a look at that. It's something that I'd like you to do together. So if one person drives Google Earth and other people look, I think or if everybody's got their own version and you're sharing one version, I think you'll find that interesting. And a lot of the things that I talked about in lecture today might make more sense when you see the kinds of processes that they've done. So that'll be what you need to work on. Okay. All right.
We're talking about the week 2 team homework, correct? I don't see a question on there pertaining to Google Earth.
Really, no?
Yeah, I don't see one either.
Oh, okay. Well, I guess that's week 3 then. Sorry about that.
Oh, okay.
Yeah, that's right. Week 2 was something else. Yeah, so you'll work on week 2. And I'm just checking to make sure that all this works. And then I'm going to go around to the different rooms and check in on everybody else. So we'll get together as a class in a second, but thanks.
All right. Thank you.
Pardon me.
Yeah, hi, Sedona.
Hi, are we supposed to leave after class or are we coming back into this room?
No, well, you can leave, or I just, we're going to go back to the regular session. I'll just say goodbye to everybody. But
Okay. Thanks.
Thank you.
okay, so
Thank you.
that's all for today. This will be recorded. There'll be a recording of this session, and you have the notes. You can look at stuff. And then we'll be getting together to finish the lecture material on Thursday. Okay, everybody.
All right.
Thank you.
Thank you.
Thank you.
Thank you.
Quick question.
A question?
Will these slides be posted on Canvas in case I wanted to go back and look at it later?
Yes, the slides are, well, there's a notes sheet which has got a small version of the slides with a place to take notes on it, and that's a PDF file, and that's in the current module for this week.
All right, thanks.
Okay. Sure. Yeah, and I try to get them up ahead of time so that you can print them out if you wanted, or have them on your phone to take notes as we go along. And people seem to find that to be a useful aid. Okay. All right, everybody. I will see you on Thursday. Bye now.
Bye.